Today we will talk about the asymptotic notations. We have learned the algorithms. So what are the asymptotic notations? So when we are analyzing an algorithm, we have to predict the amount of resource required in terms of memory and the computational time. In the terms of memory means how much space it will need for execution in our system, and in the terms of computational times means how far the algorithm runs on our particular system. Means how much time it will require for running and how much space it will require in our system. Running time grows with the size of input. If our input is less or the smaller one, the running time will be the less. Means our algorithm will be the faster one. And if our the size of particular input in a algorithm is bigger one, then the running time will be the directly proportional to the input, means that will be also be the bigger one. Input size, what is the input size in the case of algorithm? The size of an array will be the input, polynomial degree or the number of elements in a matrix, number of bits in the binary representation of the input, and vertices and edges in a particular graph. So these all are comes under the input size for analysis of a particular algorithm. Running time, definition of running time of a particular algorithm, the number of primitive operations or the steps executed before termination. So when our algorithm starts from the initial step, so how many steps it has executed before termination, that will be the number of primitive steps. In addition, will decide the running time. Coming to the operations, arithmetic operations will be there, plus, minus, multiply, data movement will be there, control statements are there, decision making statements if while loops are there, and comparison statements will also be there. So these all things will decide the running time of a particular algorithm for analysis of space and computational time in case of algorithm. We are taking an example. This is the particular algorithm for finding the minimum element for given n elements. So if we are having an array starting from a1 to an, we have to find the minimum element among the given n elements stored in a particular array. So we will give or the assign a1 or the first element to the m variable in the first step. After that, we will run a for loop for the second element to the nth element, that will be coming for the I. We are here comparing if ith element will be the less than mth element which have already stored with respect to the first element, then it will be assigned to the m. Means, and finally this particular algorithm will go give us the lesser one input among the all given inputs. So what is the running time in this particular case? Running time is again the primitive operations or the steps executed before termination according to the definition. So we will take the total running time in this particular representation Tn. For this particular first step, the assignment operation, we will take only a single one time or the space. For this particular loop, we will take n primitive operations will be there for execution of for loop. Coming to this particular condition or the third step, ai less than m, so this particular condition will be executed n minus 1th time, because the nth time the for loop will be terminated. Coming to this particular statement, the assignment of ith element to the m, this particular statement or the assignment will be executed the similarly for the n minus 1 time. So when we will add 1 plus n plus n minus 1 plus n minus 1. So that will give us 3n minus 1. This one. This particular 3n minus 1 will decide the order or the rate of the growth of particular algorithm. The order of the rate of the growth will be 3n. In this particular case means we are taking the leading term of this particular formula. The leading term of this particular equation or the formula is 3n, because minus 1 will be the lesser one, and we will ignore the constant elements in this particular case. This particular leading term 3n will decide the asymptotic behavior of this particular algorithm. The 3n, maybe the 4n, so maybe the 5n, or so on. Means in this particular case, n is of our use. So we may say this particular algorithm will run under order of nth complexity. The typical running time functions, when we see the various running time functions or the order of rate of the growth, when we see like this order of 1, order of 1 will be used when the instructions are executed once or the few times. This is saying say as constant running time. The order of 1 we may see this particular case m when a1 was assigned to the m initially. This particular step has taken only 1. This is the order of 1 type of running time function. When we see the order of log n type of complexities, the log n type of complexity will be taken in this case of logarithmic type of algorithms. Means a big problem is solved by cutting the original problem into the smaller sizes by a constant fraction of each step. So we have already seen the various example in the data structure for this particular case. Coming to the order of n times, order of n times means the small amount of processing is done on the each input element. Means for every loop we can consider this order of n types of complexity. Coming to the order of n log n type of complexity means a problem is solved by dividing into the smaller problems, solving them independently, and combining the solution that will yield to the order of n log n type of complexity. We can see this particular complexity in case of merge sort. Next one is n square, means when we see this particular type of complexity order of n square means order of n into order of n means if we are having the all pairs of data processing double times means multiple times. If we are having the double nested loop means two loops will be executed one by one or one within another one. So that will give us the order of n types of complexity. This one order of n cube, similarly it will be the triple nested loop, and rest to the power k type of all complexities will be called as polynomial type of complexities, n cube, n square, so on. If we are having this type of complexity order of 2 raised to the power n, 2 raised to the power type of complexities will be be called as exponential algorithms, or for appropriate for practical use. There are so many algorithms which will be executed in this particular time. Coming to the growth of functions, so all particular growth of functions or the complexities will be depend on the number of inputs. This is the number of input, which may be 1, 10, 100 or 1000. And if we are considering order of 1 type of algorithm, that will give us the 1111 or milliseconds or the seconds, which we may say in this particular case for analyzing an algorithm or the steps we are saying. In the case of log n, and we are taking if one input, it will give us 0 0. In the case of 10 input, 3.32, 6.64. In case of 100, 9.97. In case of 1000 inputs. Means we can see if our algorithm is executing under log n times, the particular complex computation time will be increased depends on the number of inputs. We may say, we may see in this particular again next case n times. In the case of one input, 1, 10, 100, 1000 means a particular loop will be executing the number of times as particular number of inputs given. Coming to the n log n, in the case of one input, it will give us 0 due to log n. In the case of 10 inputs, it will give us 33 milliseconds, nanoseconds, we may say, or the number of steps. In the case of 100, 664. In the case of 1000, 9970. Similarly, in case of double nested loop, we may see the increasing time or the space or the number of primitive operations. In the case of triple nested loop, we may see this particular time or the space or the number of primitive operations is increasing on the depends on the input. Coming to this particular exponential. This particular exponential type of algorithms will be the considering for the practical use. We may see in the case of one input, it is taking 2 milliseconds, nanoseconds for the two primitive operations. In the case of 10 inputs, it will be executed 1024 times. In the case of 100, it will be executed 1.2 into 10 raised to the power 30 times. In the case of 1000 input, it will be executing 1.1 into 10 raised to the power 301 times. Means this particular case of exponential algorithm will be the bigger one challenge. Coming to the complexity graphs, these particular complexities were order of 1 log n log n square, n cube, 2 raised to the power n. If we draw these particular complexities with respect to number of inputs, if this is the number of input and this is the number of steps taken or the primitive steps taken or the number of the milliseconds or the nanoseconds or the computational time, we can say computational time. Log n will be the smaller one. After that, we are having the under root n. After that, log n, under root n. After that, we are having the bigger one, order of n. After that, we are having the bigger one, n log n. N log n. After that, we are having n square. After that, we are having n cube. Means n square, n cube, n raised to the power 10. Means somewhere we are having in between n and n square, there will be n log n complexity lie somewhere. And similarly, when we are having n raised to the power 10 and n raised to the power 20, somewhere we will get 2 raised to the power n complexity. And in between n raised to the power 20 and n raised to the power 30, if we say there is n raised to the power 30, somewhere we will get 3 raised to the power n complexity. So these particular type of complexities are given as per their order or the increasing order. Algorithm complexity. So we can divide the complexity in three types: worst case complexity, best case complexity, and average case complexity. Worst case complexity, when our algorithm is running by taking the maximum number of steps for a particular size n. When our algorithm will taking only the minimum number of steps for a instance of size n. And when our algorithm or the function for a particular algorithm is defined for taking the average number of steps taken on an instance of size n, means when our algorithm will give us the output by taking the maximum number of steps, that will give us the worst case complexity in terms of order of, and best case complexity and the average case complexity. This is the graph. Best case complexity will be the best one in terms of the number of steps, means when we are taking the less number of steps and we got the output, means our algorithm is running under the best case complexity. When the number of steps higher one and our algorithm is giving the output, means the worst case complexity taking by our algorithm. And somewhere in between average case complexity will be there with respect to input size and number of primitive steps taken by solving this particular algorithm. Doing the analysis, so it is hard to estimate the running time exactly. Best case depends on the input. Average case is difficult to compute. So we usually focus on the worst case analysis. The worst case analysis is easier to compute, usually close to the actual running time. So what we will use the strategy, find a equation or the function for a large value of n is an upper bound to the actual function, means the actual number of steps, memory usage, or other primitive operations. The lower bound and upper bound is somewhere. Lower bound means best case, upper bound means worst case, and actual function will be somewhere in between that.